Hello and good afternoon, everybody. Welcome to this high-frequency simulation or antenna simulation software, add-in or plug-in in SolidWorks. So what is interesting about our product that other vendors are not able to do is to take advantage of the power of mechanical CAD like SolidWorks. It is a mechanical CAD, but we're able to integrate this electrical simulation product, namely HFWorks. The way it works is very simple. Once you install HFWorks, automatically it shows in the add-ins to SolidWorks. You just click it once, and that's it. You never needed to do it again, just once. Okay. You create your model in SolidWorks, and it's very easy. It is the #1 3D CAD package, so you can just change your model. This is a simple model, and well, 5G antennas are simple. It's just a matter of frequency, I guess, right? So if you are not using SolidWorks, you can still bring your product, your model from any other CAD package, any format, any kernel, any geometrical kernel you could simply bring. You can also bring from ECAD products from like Eagleware or Cadence or Graphics and so on and so forth. So once you have the product, the geometry in SolidWorks, it's one click away. So no exporting, no importing, no mess. So you don't have to heal the geometry because you are right inside SolidWorks. Okay. So the way it works, we use a SolidWorks concept. It's called study. And by the way, this is a gold certified product by SolidWorks or Dassault system. So it's really it's by the high standards of SolidWorks. You do new study, and study is just a design scenario. The HFWorks is a general high frequency product. You could use it to do as parameter for circuit or waveguide structures, high frequency structures. Where you want to see the scattering parameter. You could use it for resonance if your system or device if you want to study the response, the natural response of your structure, regardless of the outside world, how it is connected via ports or whatever. It's just the device itself. See what are the natural resonance mode that happens, or the antenna. Okay, so the antenna solver. This is, by the way, it's a frequency domain finite element program. So this geometry is simple. I just wanted to demonstrate to you the ability or the power of HFWorks of handling very high frequency. But the geometry is still straightforward and simple. So in terms of matrix solving, because at the end of the day, you have to invert the matrix, so you have all of these. So you have multi-core direct, multi-core iterative direct, you name it. Okay. In terms of accuracy, this one is the degree of the polynomial or the shape functions or the accuracy. We call it normal accuracy and the high accuracy. So we recommend that you start with the normal accuracy so you can run fast, because as the number of degrees of freedom per tetrahedron normal accuracy is 6, whereas in the second order the high accuracy is 20. So you can see it's 3 times the number of unknowns. It takes longer. You can parameterize your dimension, geometry, in addition to the parameterization that comes with SolidWorks multi-configurations. We have our own parameterization on top of the SolidWorks multi-configuration. Skipping 3D is really if you want to look at the port and every antenna is connected to a port. You have to feed the antenna. So that feeding, that interface that takes you from the source to the antenna, that phase where they come to, that we call the port. And the port is very important because you want to you want to make sure that you have like a 50 ohm or have matching at the port. So sometimes you don't want to do the 3D. You want to just skip 3D just to look at the port solution. Okay, the entry, the how it is, how is the impedance. You have 50 ohm, but 90% or 99% of the cases 50 ohm, but you could have other impedances. You could have 70 ohm. Some application you could have 70 ohm, but regardless, you may want to look at the skip 3D, so the 2D solution, because they do a port solution, a 2D solution to find the shape of the modes at that port. Adaptive, this is when you check this, it is going to make sure that it transitions from dense to coarse in a very nice and smooth way. And compute breakdown, okay, and most of these antennas are not high power. So in some situations, you want to see if your insulator breaks down. What does it mean? If your electric field becomes too large for your insulator or dielectric to handle it, it breaks down. Yes, indeed, it breaks down. I mean, we think about breaking down in structural breakdown, but there is also electrical breakdown when the dielectric cannot support that electric field, and then you're going to start having corona and sparking. And mind you, it's rare in the antenna application, but it's there for you. So you could sweep your frequency using a discrete sweep. So suppose I'm going to do a discrete sweep. If we're going to go from, say, 30 to 40, okay, and if I want 100 frequency, okay, and the discrete sweep is going to go at each frequency point and solves at that point. Okay, it's accurate, it's good, but it is time consuming. We don't recommend it to start with. We recommend it to start with a fast sweep. So what does that fast sweep do? It will actually solve at 2 to 3 frequencies and then interpolate using what is called model order reduction. If you want to compute the far field, and I bet you do if you are doing antennas, so you could, the far field options, especially for the gain and directivity calculations, you're going to sweep the far field theta from 0 to 180 and the fees 0 to 360. And again, you can start with, of course, the finer the step, the longer it's going to take. So it can do 2 degrees and it can do 5 degrees in the phi. Okay. Coupling analysis, you could also couple your high frequency or the antenna solution to thermal solution. So if I want to do thermal coupling, that's going to take the joule loss, joule heating due to ohmic loss or joule loss in the copper and the conductor, and as well as the dielectric, because you could have lossy dielectrics. So that's going to take the heat load or the thermal load, and it's automatic, by the way. You don't need to take any heat load, thermal load from the antenna solution to the thermal, because it's all integrated. As you can see, the previous study, I didn't have a coupled to thermal, and this one I do. So as you can see, the icon is different. Okay, and that's how the feature geometry looks like. So you get the boundary conditions, okay, and the boundary conditions are really straightforward for antenna. So port is port, Okay, so if I want to, in this case, let me go ahead and show the air, because air is an important medium for electromagnetic analysis, because as a matter of fact, that's how the wave propagates, you know. Antenna really, it's really a wave. Instead of propagating in a waveguide, it rather propagates in air in free space. So it's important to model the air, you know. So this particular case is a patch antenna fed with a microstrip. Then my port is very simple. So my port is just this. So that's how I think. Then the communication. So that's a port, and I'm going to go ahead and hide. You could have for the patch antenna, you could have a perfect conductor or imperfect conductor. If you want an imperfect conductor, choose this face here, okay, and this. And you could also specify, it is copper. You could also specify surface roughness, and you know, then is talking about 30 GHz, that's really high frequency. And the surface roughness actually could make a difference on the matching, on the radiation of your antenna. So say I want to put like 2 microns, okay. All right, for the ground. Okay. That's all you need to do. Okay. The material is straightforward. So air, you click. You could have favorite materials like air, or you could apply from the HFWorks material library, and it comes with hundreds of materials. You know, whether metals, substrates, cables, ceramics, conductor, LTCs, AECs, and so on and so forth. So it's select any of these substrates. Right. Now, if you want to couple to the thermal, if you want to see the temperature, make sure that to apply the convection. What is called heat load, due to the dielectric loss in the substrate or in the conductor, we'll take care of that. You don't need to worry about that. We do that automatically. You know, we compute the current and blah, 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 and just feed it into the thermal program. So you need to take out the convection, because the convection is, you're telling your design how effect of the air outside, you know, and sometimes you can have 4 convection coefficient. So specify the convection, and for this case, it's just the air around the antenna is really presumably in this case is cooling the antenna. Okay, so as well as the ambient temperature. Of course, I mean your antenna could be okay. That's all you need to do, really. Okay. And then you solve. Let's go and look at a solution. Okay. Yeah, the radiation boundary I forgot to mention, because you have to have radiation boundary when you truncate, because the air outside, in essence, is infinite. So you want to limit to a reasonable number of eyes, usually 1 to 2 away from your radiator. Then you have to do what is called absorbing boundary conditions. It's a smart to absorb waves, so there is no reflection from that artificial boundary, because in real life there is no such boundary, right? There's no boundary for the air. It is just open air, but we can't fit the hold the air in the memory of the computer. So do some smart mathematical techniques to truncate the air and put an absorbable boundary condition. Show you the mesh with the mesh control. Okay. As you can see, I applied the mesh control on the edges. Okay. Because by the way, could apply on a part, on a face, or edges. So most of the time it's on the edges. So that's a very powerful feature as well. All right. Now, there's one thing I wanted to show you is when I want to apply, supposedly I want to apply mesh control, wherever on these edges, we have some nice feature. We click, right? Click, you say HFWorks, and you say mesh, okay? And I'm going to select that face. Then I'm going to say extract edges. Very nicely, well, here I have a bunch of them, right? I have some like 22 edges actually. But imagine if you want to click each one of them, that it can take you a minute or two, right? But by selecting the face, no matter the edges that and you can go ahead and boom, you put the mesh control, okay, and that's all you need to do. That's also something that's going to save you a lot of time. Okay, so this is my mesh, okay, and again, it's a finite element frequency domain, so that's where you care most, okay, and the ground is not as important because it's continuous, but these sharp corners, you know, and those are they scatter, you know, they are constitute what is called singularity, and they affect your solution. So let's look at the solution now. Once it's done, I have a bunch of solutions that are generated. Okay, so this is the results folder. The results folder have the field data. So let's start with the field data. Okay, so that's my electric field. Okay, my electric field in fringe plot, I can animate it. Okay, there you go. So that's how the wave travels, you know. This is time, the phase, the omega t changes. That's how actually it travels in this one port. So it comes back. So that's how it actually travels. That's I could do also a vector plot. Okay. In this case, it's no brainer, right? I mean, this is my vector plot. Okay, so this case, so in some situation you really want to look at the vector, but in this case it's straightforward. It's a microstrip feed antenna, so it's just the vector. Okay, you could choose the frequency of your choice. You could show a plot only on a part. So if I want to, I don't care about the rest of it. I just want to see the vector plot and that and the straight so definitely faces. Okay, suppose I want to just, here you go. So I'm just showing you the plot section clipping. So suppose I want to look at one particular section. I wanted to show some of the more popular competing products that don't have this feature. So there you go. You can, it's a section. You can see move a different section up and down. And so I can up to 6 sections superimposed together. Okay, and again I can tilt the section, and so this is my tilt. I can tilt the section. I can do a lot of things with this processor. Okay, in such a way that you really know what's going on, because a lot of time in antennas we are really mostly interested in the far field, but the far field is really coming from the near field. If you don't have the correct near field, you are not going to have a good antenna gain or directivity or far field. We actually do. We don't solve for the far field, by the way. This is a secret for you. I'm telling you the secret. We don't solve for the far field. We solve for the near field. And the far field, and from the near field, we use what is called true integral, okay, to actually obtain the far field from the near field. So it's very important to be able to visualize your near field. Okay. Another feature is I can probably this time I do it in the magnetic field. I can do 3D fringe plot, and this time, okay, I could now do what did I do now? I could now do what is called the clipping, and now this is iso clipping. The iso clipping, it allows me to actually, okay, zoom in, okay, on rather on the high field. If I want to look where my high field is and how much is that value, I can simply keep zooming in and zooming in, and you know, that could very high field and some discontinuity can really indicate you problems, you know, that there's something, you know, that field is not supposed to be very high there, and then you wanna you can also show the max, okay, and you can show the mean, and then it's going to give you the location as well, okay. You could also look at the port solution, okay. In this case, this is just this port, so this is the port solution, okay. So these are basically the field data. As far as it is, it's now I can look at the results table. The results table, I have a lot of results here. So first of all, I have the antenna parameters. So the incident power, of course, it's the accepted power and the input power. Really, you characterize your antenna. Everything about your antenna is there, okay, at each frequency. Well, this was not computed. These are basically done fast sweep. So here I'm doing, by the way, 65 gig, 26 gig to 38 gig, right? So that's a very high frequency. That's why it's called 5G antenna, okay? I mean, there's nothing really special about the 5G antenna other than the frequency, of course. I mean, the shape is just a regular patch antenna. All right, so all of your antenna parameters are right there, okay? So for doing any plots, you can really look at your antenna parameter. Maximum far fields are also there, and their value and their position in the theta phi plane. So it tells you where the maximum value and where it is maximum, as well as the circuit parameters. These are, I will call, antenna parameters, really, because these are the circuit parameters. Because when you connect your antenna via the feed, you want to know is the energy coupling to the antenna or not. So you want to look, say, at S11. Are we sending a lot of, is the signal that we are sending to the antenna being reflected back to the source? Or, and that's not going to affect, by the way, your far field, okay? It's really, the shape of the far field is probably going to be the same, but the value is the how much energy you can propagate and can radiate. So it's very important to look at the S parameter or S11, return loss, so to speak. The normalized S matrix, this one with respect to the natural impedance or characteristic impedance, but this is, if you want to look at your S matrix, normalize it to a 50 ohm line. Impedance matrix, this is the input impedance of your antenna. Port results, and again, you know, when I said selected the port, really, I didn't say it's microstrip, right? So the simulator itself smartly takes a mesh on the port and solves for a 2D eigenvalue problem and find the port result. So we want to also make sure that we show you the the impedance, and this is the port impedance. Don't confuse it with the input impedance of the antenna. Okay, this is the port impedance at the port. So the VSWR. So as you can see, as you can change the frequency, and this data you can, of course, you can print it. You can print one frequency. You can print all frequencies. You can export it. You can export it to a circuit simulator. Or to an Excel sheet, or if so you say export, so I have, suppose I want to export all the frequencies, so I have in the text format, Excel sheet, circuit simulator, CIT, super compact, touchstone, you name it. So you have them, and if your preferred circuit simulator format is not there, we will be glad to, or in whichever format that you want. It's just an ASCII file as far as we're concerned. So these are basically the results in tabulated format, how you can look at them before looking at the plots. So let's look now at the plots. So what can I plot? All right, what you can plot what you saw in the results table. But if you want to look at it in a tabulated format, so I can look at, for instance, S parameters. Okay, so if I want to look at my S parameters, I can look at S11, for instance. Okay, so there you go. That's my S11. Okay. Okay, and I can track if I want. I can track my when I move the cursor, you know, the mouse is really shows me the value at each point. I can look at it in a text format. I can plot it, export it as in text format. I can do a lot of things with it after that. Okay. Now, what other plots I can do? I can also do, in addition to this parameter, all of the impedance, I can look at my unique impedance. And in this case, it happened to be the input impedance of the matrix of the antenna. So that's my impedance. Okay, it goes up to 70 ohm, around 34 gig, you know, so that's my input impedance of the antenna. I could look at, well, I don't know if you care about smooth chart, but smooth chart is there. If you, some people really, microwave people, I don't know people doing that high frequency if you care about smooth chart. But it's there. If you look at your S matrix or impedance or whatever in a Smith chart format, we have it. You got it. Okay, so this is your Smith chart result. Now, if I want to look right now at the antenna parameter, port result, antenna parameter. So what's my antenna parameter? Suppose I want to look at the radiated power. Okay, and that is very important. So how that changes as a function of frequency. Okay, well, there is some change, but not a lot. But it seems that in this particular, by the way, this for this particular antenna, the radiated power actually is decreasing as a function of frequency. Okay, and it is expected, I guess. So what else I can plot? I can in the antenna parameters, I can any quantity, any property, any like radiation efficiency. Okay, let's see how well this radiates this efficiency. Well, efficiency actually is increasing, slightly increasing. You know, despite the radiation power is decreasing, it's increasing. There may not be a very good design, you know, but just this whole idea is not to sell you a 5G antenna design. That's not the purpose of this demonstration. We're not in the business of designing antenna. We really are in the business of simulating antennas. So just showing you how we can use HFO to simulate a 5G antenna. All right, and so I can keep plotting, and everything I want to plot, I could plot all of the antenna parameters as well as the circuit parameters, because you know in this case I have only one port, but you could have an antenna feed would have many different ports. It doesn't have to be just one port for the feeding. Oh, I could also do the famous polar plot, and suppose I want to do at suppose I want to do the gain pattern, and all of this you can plot all of the antenna parameters, all the components of your antenna parameters. You can plot them as a function of theta and phi, and of course you can select the frequency. Now I'm going to stay, okay, and there you go. So this is my and again, you know, the same thing, varies. Okay, and don't ask me why it looks like that. I don't know because I didn't design this antenna. Okay, so that's but I can actually look at, and again, let me again do the plot 2D, and again emphasize again about the different quantities that you can plot. Now, some situation, you know, I want to look at the 3D fringe plot, right? That it really reflects what you saw in the 2D, right? You know, so this is your 3D polar plot. You can plot all frequencies, but no. And you can do a gray model view, and you can choose a dB, dB10. Again, you can look at different component. This one is gain. I can look at radiation intensity. Okay, I can look at all of the antenna axial ratio. Well, it has a strange look. Okay, but that's what we have for this antenna. Okay, so you have now the linear field plot, where you can actually look at the field. That's the source of all of your success or failure in terms of your design, because that's really what matters, because the scattering parameter, the reflection coefficient, the radiated field, the antenna parameter, they all depend on your near field data. So it's good to plot it. You can look at the port solution as well, and you can see results table. You can have all of this plot, whether Smith's plot, 2D plot, frequency as a function of frequency, polar plot, 3D polar plot. You can also look at the safety factor, and again, this is really for the electric breakdown. Okay, I don't know if I didn't specify anything in terms of the material, so safety factor is 1, because I have to, when I specify the material over here, edit material, you have to, well, yeah, the electric constant. Okay, so so this one we didn't compute it because we didn't ask for it in the beginning. Okay, one last thing I want to show you is of course, you want to document your work, right? So you don't want to lose what you've done. So it's really, you have a report generator. It's versatile. It can be, you can have all the information. You can pick and choose which information you want to include, and then you can personalize it, customize it, a cover page, it's a company logo, and the name and date, and then you can generate. As a matter of fact, we were able to generate, to actually import, instead of exporting a file and opening it in the Microsoft Word, we actually were successful, and we're very proud of that we're able to actually bring Microsoft Word inside SolidWorks. Not even SolidWorks are able to do that, by the way. Okay, so we are very proud of this feature, that you are actually, and it's an editable file. You can edit this file. You can write. You know, you can write on it whatever you want. Okay. It's just a Microsoft Word file. Yes, indeed, it is a Microsoft Word file right inside SolidWorks. Now I can toggle between the geometry, the plot results, and the report. If you don't want, you can of course generate a PDF, and you could also as well, if when you generate the report, you could generate an HTML if you want to share it over the internet. So all of the information of all the plots and are right in your format. So no need to take any notes. Okay, you can simply maybe print this and put in your notebook. Okay, so okay, now again, this is a fast sweep, which means solve with 3 frequency and then it operates at all other frequency. But if you want more precise solution over a frequency band range, so you probably want to do discrete sweep. Last but not least, if I want to change something, do I have to recreate, redesign the wheel, as they say? No. The answer is no, because I can simply copy 2, and I actually can copy my whole study. And there you go. Now my previous study is saved intact. And this is a CC, a carbon copy of my study. So if something is the same, the results is the same, if it is nothing changed on the boundary condition or material, or if I want to, in this particular case, instead of fast sweep, if I want to do a discrete sweep, so be it. If I want to compare the results now fast versus discrete, I simply generate another study and I can run the study and then compare. Better yet, if I want to have many studies, I can actually have 50 studies, 100 studies, and all studies. And you don't need to touch it. It's just going to go one by one, and you're going to solve all of them. And when you come in the morning, you're going to find all the results ready for you to look at. You can, in that case, for instance, if I want to, if I go back here, if I want to do a 2D plot now, because I have, well, because it didn't solve the other one, so it's not going to give me, because the other study is not solved yet. So you can superimpose results, field plots, and all of the possible data. You can compare studies. Okay. One point I want to mention also, the 2D plot I mentioned. I forgot to mention it. Sometimes you say, okay, I like fringe plot, I like color plot, but I really want to know what is happening, say, okay, between this point and this point. I don't know what, everything else is not important. This gap, okay, I want to know what happened to my electric field. Okay, and then it's just these 2 points, I can select more, and then I can actually plot the electric field or all the near field data, as a matter of fact, between in any segment. Okay, so I know what's happening. Well, I know at least in the middle of that gap, the electric field is maximum. Not only I know it's maximum, I know its value, because the color plot is nice. It gives you a good, my preferred tool as an engineer is really to be able to look at the data and say, this is the value. This is how much electric, how much volts per meter I have at the center of this gap. Okay, and if you want to look at it at the text format, then you simply just one click away. You can click. You can toggle between the plot or the results, and of course you can save it, export it, and so on and so forth. So one last thing, I don't think we have configuration in this one, but HFWorks takes advantage of the powerful multi-configuration, and that's actually what makes SolidWorks very powerful, is the multi-configuration. You can have many configurations, and the configuration is different from parameterization. In a configuration, you could actually have different dimensions. You can parameterize in the configuration, but in addition to that, in a configuration, you can suppress. Suppose I have a via that goes through the center of the antenna or a hole. I want to study the effect of that. Then I can have a configuration with and without. Okay. And the simulator is, SolidWorks is going to pull the data from the HFO is going to pull the data from the SolidWorks multi-configuration and nicely solve it automatically without you telling it, while do a new study right now, and so it's gonna study the multi configurations. Okay, I don't think time is gonna allow to go over the multi configuration, but it's rather a powerful feature in SolidWorks, and we fully take advantage of the multi configuration in addition to our own parameterization. Okay. That's it. I don't have any more thing to say. I'll be glad to take any questions. So the floor is open. And thank you very much for your time. Back to you, Adam.
Yeah, thank you, Ben, for this presentation. Let's just wait and see if there are any questions. You guys can type your questions in the chat box. And okay. So we're still waiting. Give them time to type their questions. Now, one thing to mention that attendees will be able to, all the attendees will be able to get a free trial of our software. Just have to go to our website, www.hfworks.com, and request a trial, and we'll send you a trial.
Okay. Okay, left. He says he wants to be a presenter, but okay.
No, that's just saying. That's just saying.
Okay, I don't mind to. I don't mind to take any or left to. Okay. All right. Thank you.
Okay. Thank you. This webinar is over now. Thank you all. Bye-bye.